Welcome to the Retro Lemur channel. This video is part of a series of short video demos where we cover individual assembly language topics for the Commander X16 8-bit computer. Here, we will show how to add numbers together in assembly language that are larger than what 8 bits can hold. In the first example, we will add the number 2005 to the number 4005. Here's how you would normally do the long addition in base 10. Starting from the right, 5 plus 5 is 10, carry the 1. 1 plus 0 is 1, 0 plus 0 is 0, and 2 plus 4 is 6. In 65CO2 assembly, you would do something similar, but instead of digits which can range from 0 through 9, we are actually working with a unit that can range from 0 to 255. In other words, a byte. You can even think of this as base 256. Since we don't have 256 individual symbols to represent all of the values that a byte can hold, it is almost certainly familiar to you that we represent a byte as 2 hex digits. Now, to do the math, it might be easier as a human to add the hex digits together individually, handling the carry 1 hex digit at a time, but the CPU works with whole bytes, so this is how we're going to show the math here. Starting from the right, D5 plus A5 equals 17A, carry the 1. 1 plus 7 plus F equals 17 hex. So 6010 decimal equals 177A hex. So here's the same thing in assembly. We are declaring our two numbers as constants, num1 and num2, and we can use the angle bracket operators to pull out specific parts of the number. The left angle bracket, or less than symbol, refers to the lowest or least significant byte of the number. Even though our constants were declared as decimal numbers, the assembler will just convert them to binary. First, we clear the carry. It's important to make sure the carry is clear before starting any addition operation. Next, we load the low byte of num1, which works out to be D5 hex. Then we add the low byte of num2, which is A5 hex. Carrying the 1 into the carry bit, this gives us an answer of 7A. We store the answer's low byte into memory location 1000 hex. Now we move on to the next higher byte. We're only dealing with 16-bit values, so there are only 2 bytes in each number. The right angle bracket, or greater than sign, extracts the second least significant byte of the number. For a 16-bit number, this is the high byte. We load the high byte of num1, which is 7, and we add the high byte of num2, which is F hex. Including the carry bit from the previous operation, this gives us 17 hex. We store that in memory location 1001 hex. So our assembly code performed exactly the same process as our base 256 addition, and as you can see, the result in memory after the assembly is the same as our total from earlier, 17, 7A. So what if we wanted to add bigger numbers together? Well, you can keep going. There's nothing that says we have to stop after 2 bytes. Let's do 3 bytes, or 24 bits. This time, we're declaring our constants in hex. The first steps are the same. Clear carry and add the low bytes together and store the sum. Add the next higher bytes together with carry and store the sum. And finally, the caret operator extracts the third least significant byte of a constant. For a 24-bit number, this is the high byte. For our shorter num2 constant, this will resolve to a 0, as if our number had leading zeros. We add the high bytes together with carry and store the sum. After we're done, our full sum is in memory, least significant byte first. C0FFEE hex plus BEEF hex equals C1BEDD hex. Next, we're going to demonstrate that this also works in decimal mode, otherwise known as BCD, or binary coded decimal mode. In this mode, each byte represents 2 decimal digits, which means each byte effectively represents a base 100 digit. First thing we're going to do is set the decimal flag. All this does is change the behavior of the ADC and SBC instructions. No other instructions are affected. And the rest is exactly the same as any other multi-byte addition. We ensure the carry flag is clear to start, then we add the bytes together starting from the rightmost. But this time, even though they're shown here as hexadecimal digits, the CPU's arithmetic logic unit is treating them as if they were 2 decimal digits. 37 plus 84 equals 121, carry the 1. 13 plus 42 plus the carry is 56. At the very end, we clear the decimal flag, which we should always do when we're no longer using it. Otherwise, code that follows won't expect it to be set and will almost certainly behave incorrectly. And here, memory reflects in binary coded decimal that 1,337 plus 4,284 equals 5,621. Decimal mode is mainly useful for showing scores or other decimal numbers on screen easily. It's not trivial to convert numbers between BCD and binary, so some programmers will choose to have memory allocated for both representations of the same value. For the final example, we're going to show subtraction, F1000 hex minus AAAA hex. Doing multi-byte subtraction is done in exactly the same order as addition, making sure the carry flag is the way it needs to be, then working from right to left. First, we set the carry flag. For subtraction, the carry flag is an inverted borrow flag, so setting carry is effectively clearing the borrow. 00 minus AA hex works just like 100 hex with borrow minus AA hex, which is 56 hex. Moving on to the high byte, F0 hex minus AA hex minus the borrow is 45 hex. So for our final answer, F1000 hex minus AAAA hex equals 4556 hex. One thing that may not be obvious is that you cannot trivially add 3 or more multi-byte numbers together in one pass. Since there's only one carry bit, and the arithmetic operations always include carry in the operation, the best way to sum up 3 or more large numbers is just to break it down into adding or subtracting 2 numbers at a time and storing the intermediate value, then using that value as the input for the next operation. In conclusion, we showed how to add and subtract multi-byte numbers. The process is roughly the same for addition and subtraction, and in either binary or binary-coded decimal mode. For links to playlists and other resources, please check the video description. Thank you for watching.